Alright, so here we have a look at a possible candidate for the natural numbers, which these rules, the Peano axioms, can validly generate, but as soon as we introduce addition, it becomes clear that it can't work. So this does not uniquely identify the natural numbers. It can't. So these are the rules. I pulled them off of Wikipedia. So 0 is the first rule. 0 is within the natural numbers. For some number that's an element of the set of natural numbers, something, x is in natural numbers, x equals itself. If x and y are natural numbers and x equals y, then y equals x. For x, y, and z that are all natural numbers, if x equals y and y equals z, then x equals z. Any x and y where y is a natural number and x equals y, x must be a natural number. If x is in the natural numbers, then the successor of x is a natural number. Remember, these are all axioms, so these are all just like things that for no good reason we must accept and assume. X and y are natural numbers. X equals y if the successor of x is the successor of y. X is a natural number, then the successor of x cannot be 0, so there's no natural numbers. There's no negative natural numbers. And then if k is some set and 0 is in k, every x that's in k and the natural numbers, the successor of x will be in k, thus k contains all natural numbers. Okay, that, we never defined 1 anywhere in here, other than it's the successor to 0. But we didn't actually very well define what a successor is either. So we end up with a situation where we don't have addition. So we don't have a sense that we don't have a sense of what 1 is. Okay, so on this number line here, we start off with 0. That's where we start. And we get 1 just by traveling some distance. Right? Wherever we land, that's 1. Okay? That's a successor to 0. That's true. Any point on this line is a successor to 0. So 1 can be anywhere. Okay? Now, introducing addition, 2 is the successor to 1, right? 2 is the successor to 1. Well, 1 is how far we've gone, so if we're going to add 1 to 2 to get to its successor, then what we're going to do is we're going to go this far. And now this is where we're at. So in a sense, this is now 1, right? So 2, if we're operating dynamically, we're at 2, and when we add 1 to it, what that means is we add our current position, and that gives us 3. And then from 3, if we add 1, we're going to add our current position, and that gives us 4. Right? This is a valid way to define 1, because 1 is just wherever we're at on the number line, because that's a successor to 0. By definition, by these rules, that is a valid way to look at this. But the addition rules will not work, because you end up with a situation where as we demonstrated, 1 and 2 are now equal to each other. 1 and 3 are equal to each other. You can actually get any two numbers to be equal to each other with this. So with the addition of addition, it's clear that we with this have produced a set of things that we are calling the natural numbers, which are not the natural numbers, and over which addition doesn't work. So I'm not sure what to make of that, but it's interesting because allegedly this gives you the natural numbers, but as soon as we attempt to do addition with it, with a specific definition for 1, it falls apart. There's no definition for 1 in here. So, what the hell? This clearly does not work. There's definitely shit missing from this. And personally, I think what's missing is the definition for 1. You need to be able to define your units, and you need your unit to be consistent, right? Once you're working with a unit, you need to be consistent with it, and that has to be a rule that is explicit. Because here we can set up a system where this applies, but once we try to do addition this way, it doesn't work anymore. And these addition rules are separate from what is set up here. This isn't part of the axiom, the set of axioms that gives us the natural numbers. So the fact that it's possible for this to violate what this produces, yeah, what the hell? That's a weird problem.